All right, I'll start recording because I was talking a bunch here and I forgot. So check out the stand-up math video if you didn't watch it in class. It's very exciting. Uh, that's the sort of stuff we can do, again, if we have code that simulates real life without actually having to go through and do all the hard mathematical stuff. Because real life math is hard here. And it's easy if we can just write a little simulation that is like, this is what it should look like here. Let's just do it a million times and see what happens. Um, so we can do that sort of stuff, which works out really nice. So that's one of the benefits here, being able to write simulation code. We can just run it a bunch of times. Now, our version is meant to be played, but you can imagine instead of asking the user, putting some sort of input and output, like, do you want to buy this property? We just pick a yes or a no randomly. Or we say, hey, if you have enough money, or if one of his theories was if you should keep, some of your cash in reserve, some of your value in your properties, these sorts of things here. Uh, we could write the code to make those decisions based on the current state of our player. Right? We've got lots of ways we could go about doing fun stuff and fun, maybe in quotes here, if you don't enjoy Monopoly or this sort of game theory stuff, that's okay. Uh, but game theory is also really cool, um, not just for actual games here, but used in real life stuff. But doing these sorts of simulations here, economics is really big in political science, psychology. This is supposed to be really big in poli sci. Go talk to some of the poli sci people here. Um, like apparently around the Cold War sort of times here, we did a lot of game theory stuff. There's a lot of cool rabbit holes you can get into on YouTube. Instead of getting real work done, you can watch fun stuff on YouTube. So just be careful. But game theory is really cool. I think we even have a game theory class, don't we? I really thought we had a game theory class. Hang on. This is worth looking up here now. I want the class descriptions catalog. Yes. Courses. There we go. CIS. Okay, these mention game theory. So discrete mentions game theory, discrete 2. We look forward to that. Very interesting CIS-based math class. Computer game design and implementation. Talks about some game theory stuff. And computer game design 2. Okay, so not its own standalone class, but we do get into these topics. Very exciting stuff here. Um, and it is fun. And again, I like the applicable side of software engineering, computer science. I don't really like the whole theory side of computer science, but that's just me. It's okay. Everyone has their own stuff they're interested in, and I am so glad people like writing compilers because I don't want to write my own compiler. That sounds terrible. I want to click a button and have the computer run my code and run it efficiently. Right? That makes me happy. So we can take advantage of all of that. So we fire up Visual Studio here. We unsuccessfully tried to crash my computer on Monday. It was very fun using pointers and dynamic memory. This is why C++ is a little nuts here. Ooh, Visual Studio 2026. That's exciting. I will click that button another time because that will probably take a little while. So the big hurdle we run into when we use dynamic memory is this new keyword. When we use this new keyword, we're asking the operating system to allocate memory on the heap, which is the bigger pool of memory we have, not the stack that's pre-allocated ahead of time when we start and build our program. We know exactly how much space it's going to use. Right? It's as it's running, it's going to ask for more memory. If we ask for more memory, we have to tell it when we're done with it. If we don't tell it we're done with it, the operating system assumes that C++ is still using it, even if it's not. Right? We grab 10,000 integers worth of space, right? 40,000 bytes, which is not a huge amount, but it adds up pretty quick here, and we just hold it and we never let go. We hold it, we never let go. We hold it, we never let go. So we saw it was using more and more and more and more memory here. So if you want to get rid of that memory here, you say delete. Now, the delete keyword will delete a single pointer. If we have an array or a dynamic array here, you have to say delete square braces, delete the array pointer. You'd think it'd be smart enough to figure it out here, but it's not. So be super careful here. Be sure use square braces when releasing the array. Okay, if you don't, bad stuff happens. Then we can show you, right? Why not? This was fun, right? We'll put a breakpoint in, and we should be able to watch the memory being used in our little diagnostic tool here, which is really cool. This is one of the reasons Visual Studio is really nice. It does a lot of cool stuff. You don't get all these other things other places. So right now we're not using a whole lot of memory, right? But as we continue on and do this 10,000 times, 10,000 times, we're using more memory and more memory. Let's see. Is it? Oh, did it stop for me? Maybe it. Oh, it is. Looks like it's not going up. Okay, that's handy. Let's try that. Delete values as an array. Delete it with scalar delete. Huh. Maybe it's working for us. Did not expect that to work. Right, it worked for us though. That's good. And it might be a newer feature. I'm a little puzzled, but that's okay. We're deleting. So delete is the keyword to release the memory we've used. And you can do it with individual pointers as well, right? You can delete this singular pointer, and you're supposed to. Even though it's only 4 bytes here, hanging on to 4 bytes when you don't need them is considered bad form, right? We don't want to do that sort of thing. So that's the outputted number pointer. So the next thing we do, if I delete my number pointer, that's just deleting the pointer here, right? Is not deleting the number itself, right? Because number is a variable that has some value in memory. Pointer points to that same address. So I have number and I have number pointer pointing to the same location here, right? Deleting the number pointer just says, okay, I'm done with number pointer. It didn't get rid of the other thing that existed in memory. So if I go and output number pointer here, let's actually just skip over this for a second here. I guess I can just run it. It should be pretty quick. Oh no, it's not that quick. Hang on, sorry. I'll just skip it. Let's do it like once. That'll make it faster. Uh-oh, bad stuff happened. We broke our program. This looks like some ugly thing here, but here's the stack trace. This is where it broke. So somewhere at line 32, like from my main program, line 32, it died. Right? And if we continue on, uh-oh, it failed. Oh goodness, I can't even click that. It's real sad. Come on. Debugging the heap here. If problems in the heap. Valid heap pointer. Come on. Come on. Just let it die. Yeah. It broke real bad. Doesn't like it. But you can see it's warning us down here. We've used uninitialized memory. If we go delete this pointer here, the compiler knows, hey, you just deleted something and you're trying to use it. Bad stuff happened. Right? So, and be careful with your deletes when we deal with pointers. It sounds complex, and it is. It's one of the reasons you can do really cool stuff with C++, and also you can shoot yourself in the foot with C++, because it will let you do bad things here, um, like accessing bad values, all sorts of trouble we get into here. It can be sort of I don't know, risky. You really have to know what you're doing, right? Again, another plug for we don't just copy paste code in because we don't really know what it's doing, right? You have to know what the code is doing here to make sure we're doing it the right way and not running into issues. So this is dynamically allocating objects. So not only can you do pointers for, say, like integers, but you can have a pointer for an object of a class. Like we spent a bunch of time writing classes here, so you can make a pointer to an instance of a class. Now that class will be allocated on the heap here. Doesn't seem like we've gained a whole lot here. That's okay. It's not all that interesting to do it that way. Um, when we start using pointers, we have to write our code differently. It's real obnoxious, but that's okay. So let's go. Let's go copy paste like the chair class here. So that'll be a little bit faster. Let's see. Go. Just steal it out of here. Oh, let's do chair. I think chair was right in here, right? Yep. So here was chair, gets and sets. All right. And we'll just go dump this on top here from last week. All right, close enough, right? You know where that was coming from, right? Uh, if I want to make a pointer for a chair here, so hey, I want a chair pointer called Eric's chair, right? I've created the pointer. We've allocated space for it. We haven't assigned it any values yet. It's still uninitialized. Then we can go use that new keyword, or all in the same line. You can say equal to new chair. We use the new keyword, allocating new space in memory that didn't exist before. There's no constructor for chair, right? We didn't add anything here, so we have to go set all these values. But because it's a pointer now, I can't just say Eric's chair dot. Oh, no, sorry. When I hit dot here, it gives me the suggestions because Visual Studio knows what I'm trying to do here, and it's going to auto-convert for me. So when I say, hey, I want to set color here, notice it changes it to a dash greater than sign. This is the arrow notation. So if you're using pointers with functions, you have to use the arrow notation, not the dot notation. If we created objects on the stack, we can use the dot notation and not the arrow notation. I don't know why. Someone came up with it here. But right, this is a pointer, and we're pointing at this function, is the way I like to remember it here. So if you're using pointers, use an arrow to point at the thing. I don't know. That's the best I got here. So we'll set that to blue, right? Great. Now, if I just, again, if I make another chair, so chair, I don't know, Jeb's chair, right? Actually, I only need the parentheses, right? Jeb's chair dot set color, right? Black. And the syntax is a little bit different, right? So dot with our regular objects, arrow notation with pointers, right? Again, it doesn't seem super useful to make these pointers here, but being able to put stuff in the heap memory is useful. We can do more things in the heap here. Eventually, our programs will get bigger and more interesting. Eventually, right? We're just not there yet. Everything will fit perfectly fine in the stack, but you do run out of space eventually in the stack and need to move over to the heap here. I think it depends on your operating. I don't know how much can you use in the stack versus the heap. Let's see if there's a good answer for it here. Does that give us anything? Yeah, you get a Stack Overflow. That's in Java, but there might be a website named Stack Overflow. Okay, you've heard of it. Okay, it's named after that happening here. So heap dynamically. Yeah, you can get out of memory. That's fine. That's Java though. Um, no, not doesn't really give us a whole lot of other stuff here. Stack memory, heap memory. There's a fun diagram. Sure. You have to do it manually, right? Costlier, but more likely to run out of memory in the stack. Right? We talked about that. Less space. It doesn't tell us how much room though. It didn't give us a max number. I don't know how much it is. It's less though. All right, that was very exciting. Sorry, we did not find a good answer. Maybe the AI bots will answer that for us better, right? I'm sure it won't make up anything. They never make up stuff. All right, the last bit here that's cool with pointers, and this is one of the key reasons that pointers are better for us to use. We haven't got to it yet, and I'm just going to show you a silly little preview here. It's the next chapter here is on inheritance. Inheritance is a core fundamental principle of object-oriented programming. It lets us take something and make a custom version of it, inherit from it. Right? We're familiar with inheritance if you're like biology, right? We inherit things from a parent here, or this parent class, you inherit from it in a child class. Okay? So you can be one of these things here, but you're a specialized version of it here. So instead of having to rewrite someone's code as, hey, their chair class was great, I love everything about it, except This new chair class has a motor in it because why not stick a motor on things so I can drive my chair with a joystick? Because that sounds like a lot of fun, right? I don't want to have to rewrite chair. It already has a color. It already has the number of wheels. It already has all this attributes. It can go up and down. All I care about now is I can drive it, right? I don't have to reinvent the wheel. So I'm going to inherit from chair to make a specialized version of chair that's a motorized chair, right? So we're going to use inheritance lots of places. It's a good tool. We don't use it everywhere, but it allows us to make custom versions of things here. So we can make another class that inherits from chair that is a chair, but it's a special version of chair. So I can make a motorized chair given chair. Oh goodness, I hate the syntax here. Can you run it? Oh, sorry, colon. Of course, C++ is silly. That was Python syntax. That's what I'm doing wrong here. Public chair. Okay. This class inherits from chair. It is a chair here, but it has all these functions here that chair has, but now I can add special stuff. So I can have my own private section. I can have my own public section here, like void drive. And we're just going to, I don't know, the out room. Terrible example here. My apologies, but that's fine. We're just going to output room. That's the only thing motorized chair does. So, and a semicolon. Thanks. If I make a motorized chair now, motorized chair, pointer, we'll call it a, I don't know, fancy chair, equals a new motorized chair. Now, fancy chair dot, I get all of the things that came from chair. Because I've inherited from chair, I have all of its public functions. It is a chair, it does all these other things, but it can also drive, which is fun. So I've got all the things that it does here and my special version. So I can call drive whatever I want to do here. Right, and that'll just room when we call drive. Right? Now, we can make another kind of chair here. Let's call this, I don't know what, a floating chair, I guess. There's a funny video. Someone was like, hey, we're going to improve our office productivity. So we put my office workers in a pool to make them happy. And there's like, they're working on laptops in a pool. It was some dumb video. It was really funny, though. Right. And this one is when you drive, it says splash instead of room here, right? Because you're a floating chair. Now you can splash instead of room. And we'll do this again. We'll make a floating chair, I guess, with a floating chair. And called it floating chair. And we'll take our floating chair and we'll drive that one here. And that one should splash. So we'll vroom the motorized chair, we'll splash the floating chair with our pointers. Doesn't seem very interesting yet, but we're getting there to the magic part here. Okay. So now this will vroom, this will splash. Right. The last thing I'm going to do here is I'm going to add a drive function to chair, void drive. That does nothing. You can't drive a regular chair. It's not motorized and it doesn't splash. So what I can do is I can write a function here. We'll make a void function. We'll call it drive chair, given a chair pointer here. Call it a chair. And all this is going to do is say chair.drive, arrow drive, right? So if you give it a chair, it will call the drive function on it, okay, given a chair pointer. Okay, so if I call my drive chair on Eric's chair, nothing should happen, right? Because chairs don't drive. Okay. The other cool thing that inheritance lets us do is because motorized chair is a chair, I can give a motorized chair in place of a chair. So I can call drive chair given the motorized chair, my fancy chair here, right? And I can also call drive chair given my floating chair because it is a chair, right? And what's going to happen is it's going to call the drive function. So when I put a breakpoint in here, right, we're about to drive the chair, right? This was Eric's chair here. And if I step into my code here, we get nothing. Right? Chairs don't do anything. They don't know how to drive. Now we're going to drive the fancy chair. I step into this one here and step into drive, and it goes to nothing. Uh-oh. It's a chair. right? It's called the chair version of it here. We try our floating chair. We call drive on our chair. Nothing happens. We got nothing on them. It's not calling the right version here, right? We told it, hey, here's a chair. You should go do your chair thing. It's calling the nothing version, right? So there's a way we can fix it. When we write our functions here, we need to tell C++ that it's okay to do something different. And we'll get into this more next semester, just kind of introing the topic because it's interesting and one of the benefits of why we have pointers here. We're going to say this is a virtual function here. And then when I make these functions, I'm going to say they override. Override here. Void drive over. Is it on this side? Override. Override. There it is. Override. So now when I run my program, just by adding some keywords here, by telling C++, hey, this thing is virtual, which doesn't really mean a whole lot here, but that's okay. We get nothing for Eric's chair. It doesn't know how to drive. That's fine. We drive my fancy chair. Now it says, oh, this was virtual and there's an override. I'm going to go do the thing that it actually is. So while the program is running, C++ can understand that this function asks for a chair pointer. What it actually is in memory has an overridden definition for that function here. I'm going to do the actual thing it's supposed to do, not the chair version. So it's able to, at runtime, figure out which type of pointer it actually is and run the correct version, which is very exciting, I promise. So in the floating chair, we go drive it, and it says splash. Hey, I found an overridden version here. So we get some cool keywords that let my program, while it's running, figure out what actual kind of class this is here and do the right version of it. Okay. Without pointers, it doesn't work. So if I just say, hey, I want to drive regular chairs here, so this is chair dot drive, and then I can dereference my pointers, right? So dereferencing a pointer says give you the memory address of where it is. Right? So now when I run using my objects here, let's drive, 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 we get nothings again because we're using objects, not pointers, two objects. Seems a little silly here. This is one of the cool features of C++ here, that it will do the right thing. And our technical term for this here is polymorphism. So it's a big fancy word here, but it's a lot of fun. It means we can treat child classes as their parent class, right? We can treat a different type as its parent type here. And that's why things can always see out. Like when we were to see out an object here, when we wrote a chair, right? If we just did a see out on chair, or on Jeb's chair, right? Remember see out works here, but you get garbage. Remember we did this one here, didn't we? Uh, oh goodness, do we have to do, how do we convert it to a string? Two string or something? Oh man, I forget. There's a, where's my see out here? Yeah, that's fine. Never mind. You get garbage because it doesn't know how to do it, right? But it knows how to see out eventually. All right, that was very exciting with pointers here. The rest of the chapter here, go ahead and read through it. There's not too many things to do with the labs, so 2 little practice labs should be fine here. Give them a try. I think you can get them done. If you get stuck on something and you just are frustrated and want to give up, that's fine. Attempt them, and I'll give you the points for it. Is that okay? Ideally, you can get it done to be good, but I won't hold you to it too much here. Smart pointers clean up after themselves. Right? We don't have to go delete them. Thankfully, someone realized that's a big pain in the butt to have to do here. Not everyone has shifted over to using smart pointers yet, so we still have to teach how to do it the old way and remember to delete them. The new ways, we just use a smart pointer, and when we're done with it, it deletes itself. Thankfully, computers are kind of smart, at least a little bit here. Um, Other things like destructors we'll get to next semester, copy constructors we'll get to, copy assignment operators we'll get to next semester. This rule of 3 we'll get to as well next semester. So I think just the first little bit here, some dynamic arrays is fun, deleting stuff, and then further down the road, know that it works with this inheritance stuff, and we can do really cool things with pointers that you can't do without pointers. So if we're not using pointers, you can't take advantage of polymorphism, which is a big downside here because that gives you a lot of advantages, a lot of nice, cool shortcuts here. Um, that might not sound super cool, but if you can imagine writing a large project here that lots and lots and lots and lots of people have to work on here, more than just you and a partner, maybe, right? I can say, hey, you give me something that has a drive function. You figure out later how what drive is supposed to do, right? Someone on another team somewhere, or someone else that I probably might never even talk to, will write all the stuff for drive, but I want to make sure that their version of drive works, and I don't want to have to write a different function, right? That's why polymorphism is important, right? So that someone else can define something here. We just say, hey, I know it's going to drive. I don't care the details. Right? This idea, we want to work with things abstractly. I don't need to know all the details of how a class does it. I just know it does what it's advertised. It drives. Right? Someone else can figure that out here. And then pointers and polymorphism allow me to make sure I do their version of drive. Right? So they can set all that up here. All right. I think that's actually pretty good. So we got through pointers here as much as we need to for this purpose. We got Thanksgiving break next week. Don't come. You'll be lonely here on campus. Um, the week after that, a couple last minute topics, right? We got to hit recursion. We got to hit some UML stuff here. I'll talk to Dr. Saeed. Hopefully, we can get a practice in for that one. Um, and then 12:8, I have no plans to talk about anything. I'll just show up and answer questions here. If you have questions about your final project, again, you're welcome to work with a partner if you want. If you don't, that's okay too. You'll have plenty of opportunities for group projects in the future. Don't worry too much about it. If you can get it done by 12:8, good for you. And then you can focus on your other classes, other finals that you have to memorize a bunch of crap for. All you'll have to do on the 15th is show up and run it. Show us you can play a game, you can save it, you can load it, these sorts of things. I might have a question or two. It takes less than 5 minutes for most people here. 5 if you like to talk a whole lot here. And if you do something cool, show us, right? I want to see the cool stuff, right? What did you do that was really interesting in your project? It's a lot of fun. Talking in front of your peers is something you're going to want to get used to. That's one of the reasons we practice it, right? If you work in a group of developers, one of the things you'll do is show them your code. Hey, this is what I worked on. This is what it does here, and you'll get some feedback. Right? Feedback is good. It helps us improve. It's okay to make mistakes, right? I get this is a little bit high pressure because there's a grade attached to it, but hopefully you'll know what your grade is going into it because it works. I'll gotta add the rubric for you. That's right. I did not add a rubric yet. Let me go add that in for you here. So we'll do the same idea. So tell me how you did with your rubric here. So we're for 40 points. This is final project. Excuse me. So we have variable number of players can play the game. Excuse me. And use its classes for players and properties. Gameplay works here, and then saving and loading. Loading works. Again, if you want for save and load, it could be after every player. If you want to just say, hey, before player one goes, everyone has had a turn. Now you can save and load or save the game and quit. That's fine too. That makes it easy because then you always know player one's the first one to go when you load. That's okay. That's a nice, easy shortcut, right? Rather than, oh, it's player seven's turn. I need to remember to start with player seven instead of starting back in player one, right? Both ways can work, but if you start with some number of player, you have to tell the save game which player's turn it is. There's just one more piece of information to save. So if in your menu of when you play the game, you only let them save before player one, that's fine. Right? That's perfectly acceptable. That's probably a nice, easy shortcut here. So when you load the game, I just read off some number of players, start with player one, right? I've got my properties, I'm good to go. So we got some choices. Figure out how you want to write the file or how you want to read the file. Either one of those two will determine the other one here, whichever way you want to go. Perfectly fine. So some number of players. We've got our classes here, nice object-oriented programming, private attributes, public functions, right? Those sorts of things here. The gameplay actually works. We can go through and do those things here. and saving and loading for the 40 points. So hopefully you know how you did well in advance, right? Um, it's got to have 10 commits over 10 separate days. Now, someone did ask me in my other class if they're like really in the zone and just working at it 8 hours straight, did they make more than one commit? And sure, like if you're working that long, give me 2 or 3 commits in a day, once or twice, right? Is probably okay. But we want to spread it out here. We want to show the commit history is the goal here, that I've built incremental working code. Yeah. Do people do 10 each or 5? 5 each is fine. Yep. Yeah, if you're working with a partner, that's okay. 5 each. Just to show you've split it up, you've done some work here, and it should be runnable at each step of the way, right? It doesn't have to do everything, but it should run in like when you have the menu, you just don't do that part yet. Right? Hey, do you want to buy a property? Sure, I want to buy. Oh, I don't know how to yet. Well, that's okay. At least that shows up in my menu. I can have a list of properties. I don't know how to make you buy them yet, but I've got this part working that I can test it out here. I can move around the board. Like, you want to think about how we take a big problem, break it down into smaller and smaller and smaller steps here. Save the hard parts for later. That's okay, right? Just do little bits at a time. I can do this part. I can do this part. I can do this part. I can do this part here. Hey, I'm going to charge you rent, but I'm not actually going to take any money from you. That's fine, right? It's cost $10, but we'll figure out later how I take 10 from you and give it to someone else, right? Those sorts of things. That's good incremental progress, right? And that's the goal. It's a good habit to learn to develop like that here. So I'm going to make you do it, right? Okay. Sound good? Awesome. So I will see you in a week and a half or so. Have a great Thanksgiving and take care.